All right. In the interest of time, I think I'll start so that we can perhaps fit in the 15-minute window. So my name's Brett Lovgren. This work came out of a time when I was a long-term sub at the American School of the Hague, working in language arts and math. This happened to be a seventh grade statistics and probability unit that I was teaching. And so it was, over the course of a year, coming up with a way to introduce the Monte Carlo method to seventh grade math students. So just a quick background, what is the Monte Carlo method? So it's generating random numbers and observing the fraction of numbers that obey a certain property. And so we'll see an example of this and sort of some historical background in a moment. So another sort of background knowledge that you need is what is experimental probability? So the ratio of number of outcomes of a specified event to the total number of trials. So the simplest way to think about it is if I flip a coin and it shows tails 3 times out of 10 flips, then my probability of getting tails, my experimental probability of getting tails is 3 out of 10. And so you'll see when we get to the next the lesson plan itself, the utility of these two details. So here's the man of my presentation who invented this process. Stan Ulam was a physicist and mathematician involved in the Manhattan Project, and they were interested, as you might expect, in the path of neutrons going through fissionable material. And so he was tasked with understanding the propagation of these interactions through through this fission core, this bomb that they were designing. And so one of the things that was interesting to me is there was an oral history done years later, and they interviewed Stan Ulam, and he said, well, we were interested in this branching process. One neutron makes a few more and a few more, the mathematics of that. And so this Monte Carlo method was invented to understand that process. Now, one of the things, I won't take the time to play the video right now, but Stan Ulam's boss, Ed Teller at the Manhattan Project, was actually concerned. One of the reasons that he had tasked Stan Ulam with understanding this propagation process was that they were worried that when they set off the atomic bomb, that it might light the atmosphere on fire and destroy everything, right? So it's kind of amazing, Ed Teller says this rather casually in this interview, and you think, oh my goodness, imagine the stress of, some physicists and mathematicians involved in the Manhattan Project, and one little branch of them is concerned about lighting the atmosphere on fire. It's kind of staggering to think about, just the stress that they were under in something that at the time they were inventing. They were literally inventing this entire thing. So it's really a remarkable history. And for me, this was kind of the hook, of why does anybody care about this and why are we doing it? So it was kind of fun to come across this history. And when I initially did the lesson, I didn't know this history, and so it was fun to go as I iterated through the lesson to find this historical detail. So the lesson itself, the sort of core of the lesson itself, is we're going to estimate the value of pi using our knowledge of this image and a random process of dropping a pencil on the image and looking at the ratio of the number of marks that occur inside the circle versus the total number of marks on the image. And so, for seventh graders, that's a pretty straightforward thing. It's easy for them to understand. It's easy for me to understand. And so it was really fun to kind of start with this proposition and then, put them in their table groups and give them a giant poster board and pencils, rulers, compasses, enough materials for them to copy the image. And, we talk a little bit about the prior knowledge that they're going to need in the investigation. But, essentially off to the races, right? They they start with this image, and then they start the process of this random sampling technique of, well, let's make a random dot on this image. And what was kind of fun to watch was their enthusiasm in, coming up with this random, what some of them came up with a random process, and some of them came up with a non-random process, and we'll talk about that in a minute. So there was a lot of standing on desks and chairs and, trying to get as high as possible over the image to drop their pencil on it. And then there were a set of people who got very bored and decided that they needed to collect more pencils. And, can I drop 30 pencils that I've collected all at once on the image? And, there was the random person who comes up to me and says, how many times do we have to do this? Like, what's a good number? Well, good question. And there was also the entire class, somebody put the poster board on the wall, tacked it up on the wall, and everybody at once threw their pencil at the image, right? So it got very creative and very animated. And so that was kind of part of the fun of the activity. So here's the actual lesson itself. So you're estimating the value of pi using your knowledge of the image below and a random process to drop dots on the image. Now, what's interesting is very quickly, let's look at this image. So we're interested in the count of marks inside the circle over the total number of marks on the image. And we're making the proposition that that's equal to the ratio of the area of the circle over the area of the square. And what's kind of fun about that is, if you think about it, at the limit, if I have 1,000,000 dots on this image, well, it is the area of the circle and the area of the square, right? If I completely fill the image in, it is the area. So it's kind of nice that, this equation sort of makes sense, right? And then we're using prior knowledge about, well, what's the area of a circle? Pi r squared. What's the area of a square? The side length squared, right? And it turns out that in this example, right, twice the radius is the side length of the square. So you very quickly get to this place where you can cancel out some values and end up with 4 times the ratio of the marks is equal to our estimate for pi. And that's a kind of lovely and simple equation to understand. And so here's an example of one of the the work of one of the table groups, and you can see the enthusiasm. Some of the marks go through the paper, right? That's when you're really throwing it hard, and so it was just lovely to see these table groups, and their enthusiasm. And do we need to measure the length of the side? Well, turns out no, you don't actually need to measure, right? It turns out that this works by counting up the number of marks inside the circle and the total number of marks. And so you end up with, here's some estimates from a particular class, right? And, you can see it's sort of in the ballpark, right? We're not totally off in some crazy estimate. Now, part of what's interesting is when you get into the group of people who grabbed the 30 pencils, well, it turns out that that's not a random sample, right? Because you've grouped them together, so they ended up making marks in a non-random pattern, right? And so their estimate for pi was off because they had not sampled randomly on the image. And so that was a kind of lovely detail that we could talk about. Now, if if you're interested in sort of joining along, there were electronic versions of this, and you can play with the simulation yourself. Let's see, I can drop this into the chat, and so you can run this simulation and see an estimate for pi, using various sample sizes. And then you can also fill in this form if you'd like, copy that in. And so you can contribute to the estimate for pi. And this was an example of, running that simulation a number of times. And you can see, that at the 5,000 iterations of it, we got sort of reasonably close to 3.14, right? But other estimates are, in different age ranges. And so you can, it's one of the things that's interesting about this random process, right? Is that hopefully, as we would collect more data and do more rounds of the experiment, we would begin to approach 3.14 for our estimate. So I, wrapped up the lesson, going over some of the details of collecting a random sample, some of the issues with the bias of the clustering of the pencils over the image, talking more about experimental probability in our estimate, and then I over the course of multiple rounds of the lesson, I collected lots of questions that came up in the course of the lesson, and also looked at the sort of scaffolding that you could do for the students who just needed more time to sort of work through what we were doing, and maybe weren't familiar with the area of a circle and area of a square, and so this was just it was lovely to sort of collect, going through the iterations of the lesson to collect the questions and the scaffolding. So that was it, and I'll leave you with the daily commute here in the Netherlands. This is when I would think about what the lesson was going to look like on my daily commute to work. So that's how this lesson came about and the evolution of it. So thank you for listening to the Monte Carlo method lesson.
Thanks for sharing, Brett. I love that commute.
So do I. That's one of the treats about living in the Netherlands, is that it's easy to commute by bike.
Yeah.
Thank you. Very interesting.
Thank you.
Thanks. It was really interesting, fascinating. Thank you.
Great. Thank you. Any questions before we go?
Hi, Brett.
Yeah.
Hey, my name is Brian. I'm a new graduate student at TCMJ.
Oh, great.
And and I also work at the Sarnoff collection at the college, which is material donated by the heirs of David Sarnoff of two little companies called NBC and RCA.
Okay.
And also I have this background working in modern and contemporary art, and a lot of the practitioners in those fields have worked in more or less informed ways in mathematical procedures and geometry and so forth, or so they think they were. And I'm not exactly a math specialist myself. One of the challenges I've had is interpreting for variously skilled audiences the work that these artists did. A lot of procedure-based activities and so on. Anyway,
can I stop you just for a second?
Yeah.
Are you talking about sort of generative art where it's algorithmic, or?
Yeah, more recently, yeah, I've curated exhibits and worked with a bunch of artists who do that sort of thing, up to and including some at least rudimentary AI-oriented projects. But even way back in the 20th century, artists were using their notions of geometry and other mathematical procedures to develop abstract work, for example.
Okay.
And the challenges I've had is that, not being an expert myself, trying to be in the middle of artists who weren't always clear on what a lot of them have pretty idiosyncratic ideas
Right.
about the
They
first
were artists.
principles. And a lot of the audiences also have no idea. And so here I've been in the middle with my MA in curatorial studies from the late 90s.
Yeah.
Anyway, this project was just so excellent and so straightforward. I love the image of the table groups board with the impact of their experiments.
Yes, the enthusiasm. Yeah.
Absolutely, yeah. So just to say thank you, and this is the sort of project that even a non-specialist like me could imagine using in either a classroom setting or some sort of museum education program setting. I mean, I'd love to see people standing on chairs in, a museum classroom dropping stuff.
Yeah, it's I mean, part of what was remarkable to me was how long it took to get to this place. It took the better part of a year teaching the statistics unit for me to
Right.
finally be in a place where I felt I could introduce the Monte Carlo method. And so, it's to me, it's no small thing to get to a place where it actually works, where you've distilled it down to a place where you can introduce the idea, the area of a circle, the area of a square. The seventh graders are perfectly comfortable with that. And
Right.
then this idea of, well, let's do some random sampling on the image, and can we combine our prior knowledge about the areas to come up with an estimate for pi? And it was a lovely kind of sweet spot where there's just enough of their background knowledge plus this introduction of experimental probability, where kind of anybody, even without any background in statistics or probability, is kind of comfortable with the ideas. And for whatever reason, I just feel really enthusiastic. So I appreciate you.
Yeah. So in retrospect, do you think that you could have introduced this a bit sooner?
Absolutely. It was really me. It took me personally the year of teaching this class to finally get to a place. I mean, literally, this was like the last week when I did this lesson. And it was just really rewarding, because there was, as you see in the physical artifact, this enthusiasm for it and understanding. I mean, when their estimates for pi came up really close, they were like, "God, this is cool." So I just loved every aspect of it, where it's the physicality of it plus their enthusiasm and this tangible result that everybody can recognize, right? And so I mean, I love this this crossover of the math with this kind of, I mean, it's interesting to think about it as an art object, right? Because they were, one of the things I did is I collected all the physical poster boards.
Oh yeah.
And it was just fun to sort of see them, because they're all working through their ratios and their counts and everything. And so yeah, it was just a lovely lesson. And to me, it's amazing how much can go into an hour and 15 minutes of work. It's really so thank you for
oh yeah, for sure.
Yeah.
Yeah, thank you very much. And I too am jealous of your commute.
I appreciate it every day. It's when I come around a corner and there's a sunrise, I just think, what?
Yeah.
Awesome.
Well, I live in Philadelphia and I commute to the College of New Jersey, which is, I mean, to say that is bicycle unfriendly is a radical understatement.
Yes.
But anyway, I don't want to end on a negative note, so I'll just say thank you so much
Yeah,
for
thank
the
you.
presentation. Yeah,
You're very
yeah,
welcome.
yeah. Take
And
care.
so are you a student or a teacher, or what's your role?
I know, right? I'm old enough to be a teacher, but I've worked in museums on and off for about 25 years, and I've just started in teaching English as a second language certificate program at
Oh,
the college.
congratulations.
Yeah, thank you. Yeah, it's been terrific. Dr. Wu and Megan both urged me to participate today.
That's great.
Yeah, yeah,
Thanks for dropping in.
of course. Yeah. Thanks again. See you.
All right. Yep. Bye-bye.
Bye.